Okay. We are in the final home stretch of the course. Okay, we are about to start differential equations, okay, which is the last of the material that is fair game for the final exam. Okay, and we got enough chirps from the other classes about wanting to get the old finals up sooner rather than later. Okay, so I have done that. And so let me review briefly. Coming down to home stretch, what you are responsible for here. So for example, last year, fall 2012. All right, so here's what we did last year. Okay, and again, similar format, 5 problems, 100 points each. You will have a problem that is a sketching kind of problem. Okay, big difference between this and exam number 2 is you'd be given a plot and then some initial conditions, right? And that's it. No information about anything besides initial conditions. So in order to do this, right, given your results, use derivatives and or integrals to plot, the next function. So starting with acceleration, plot velocity, indicate maximum, minimum, final values on your graph. All you're given is initial conditions. Okay, so you can't do a problem like this unless you are using concepts of slopes and areas. Okay, and so it's the kind of cumulative use of calculus, derivatives and integrals to sketch stuff. Okay, so that's one. Then you will definitely have an application of integrals. We did, applications of integrals in dynamics, applications of integrals in circuits, application of integrals in statics, etc. So this was a circuit application. Looks like an inductor problem. Again, knowing that this is true and the initial condition, find I of t. Okay, and so it's pretty clear, right? If this is the derivative of I, in order to get I have to integrate both sides. Okay, and then the ability to sketch whatever it is you get. If you look at this, the given function was a trig function. It was cosine. All right, so being able to integrate a cosine, get a sine function, be able to sketch a cycle of it, that was on there. And then here's another one, another sketching kind of problem. Again, these are all electrical applications of integrals. Right, sketch the voltage across the capacitor. Again, time is measured over here in milliseconds, so more sketching. Okay, sketching the power, P equals V times I. So applications in dynamics, electric circuits, being able to sketch things using areas under curves. Centroids. Okay, application of integrals in statics. You'll definitely have a centroid type problem. So this one was a gear tooth. Right, determine the height and width of the tooth. So how do you find the height of something like that that's given by an equation? Suggestions? Anybody? How would you find the height? Yeah, you got to find the flat spot, right? So that's a derivative question, actually. It's the final exam, right? But that's a derivative question. Got to find the maximum value. That's the height. How about the width over here? Yeah, I mean, this is the roots of the equation, right? Look at the equation. It's a parabola. Right? And so what are the roots where it's equal to 0? One of them is going to be at 0. The other one over here is b. Okay, so again, questions were, is the final exam going to be cumulative? Well, I mean, fundamentally, this is a problem where you're trying to find the area by integration, the centroid by integration, right? X and Y coordinates. It's a centroid problem, but we're good at asking you questions that means you need to find a flat spot or you need to solve a quadratic equation, right? So the extent to which basic algebra is still needed or I need concepts from derivatives to do problems, that's all fair game kind of stuff, but clearly the topic that we're addressing here is centroids, right? And so that's the point. So it's cumulative in that respect, but again, applications in dynamics, applications in electric circuits, applications in statics, that's the first 3 problems. on the exam. If you look at the other 2 posted exams, that's the first 3 problems on those also. Okay, so the topics are clear, right? The things we did for the homework sets associated with each of those. And then there will be 2 problems that are differential equations. Okay, so we've got the rest of the course on this. Now that's a couple lectures this week, 1 before Thanksgiving, and then we wrap it up right after Thanksgiving. Okay, that's how we're going to handle differential equations. And so it turns out that there's what's called first and second order differential equations. We'll talk more today. But this one, I think this problem made the revised preliminary edition of the textbook. Okay, so here it is. This is the Wynn-Kessel model. It's a biomedical engineering example, okay, for blood pressure in an artery. Okay, and it's an equation for pressure, and it's got a first derivative of pressure, and it's got pressure, and it's got a volume flow coming into the artery. So again, we're going to work problem even today pretty darn similar, you know, to this. The leaking bucket that you guys did in the lab last week, okay, is very similar to this governing equation. So understanding how to solve that, what are the steps that you take, you'll have a good sense of that by the end of even today's lecture. Okay, but all we're going to do for the next, whatever it is, 5 lectures is more how do you solve differential equations. So it gets pretty straightforward. Okay, but again, the application could be, you know, whatever. This was a new application. Class had not seen this Wynn-Kessel model before. So feeling comfortable being able to apply what you know to whatever the situation we give you. Okay, and so solving these things is a bit like a recipe. There's these standard kind of steps. Okay, and so those steps many times are laid out right in the question. Okay, so as long as you're, you know, sticking with me during lecture, working the homework that we're going to do, practicing these exams, differential equations is really not a difficult topic. It's just a topic that requires mathematical perseverance. Okay, that's what I would call it. You know, the solution might be an entire page, page and a half, 2 pages of handwritten stuff. It's not hard, but it's just you got to be methodical and you got to work through it. Okay. All right, so that's it. And then here's another one. This looks like another electrical one here. This is what's called a second order differential equation because the equation has a second derivative in it. Okay, so you will definitely have one problem that's a first order differential equation and one problem that's a second order. And whether or not it's electrical or whatever, biomedical, mechanical, whatever we cook up, doesn't matter. So solving these problems is the same no matter what the context. Okay, so that's it. And so working through the whole solution to that. Okay, and we like to do some of these kind of things on the final, right? You can look and see what we've done in all 3 posted ones, but, you know, ask you these kind of like qualitative questions, you know. Suppose the forcing function is now this instead of that. You know, what would happen, right? What's the value of the frequency that would cause the solution to increase without bound? Okay, so these are results that you would understand as we progress in the next couple weeks on solving differential equations, okay, and types of behaviors that are possible. So we tend to do that a little more in the final, asking you to explain something or something physical to draw from the net results. Okay, so and just like, you know, the rest of what we do in here. So you look at what the solutions entail. So there's a sketching problem. There's the electrical problem, and then a little more sketching. Here's the centroid problem. Typically takes about a page of calculation. Here's a first order differential equation. And here's the second order one. So in terms of length, level of difficulty, it's the same deal, right? You look at the last 2 exams you've already taken, the solutions that were posted, all the prior posted exams, pretty much the same. Each solution's about a handwritten page of calculation for each one of these things. Sometimes the differential equations problems can get a little longer, but for the most part, level of kind of length and difficulty, you know what to expect. You've been through 2 exams in here already, okay? So the other difference in the final exam is we do this during the unscheduled block, 1 o'clock to 3 o'clock p.m. on a Thursday. So this could be good or bad. If you're a night person and you really love the 8 to 10 p.m. exams, well, now you got to adjust to an afternoon exam. In general, I don't think people are that huge a fan of the 8 to 10 p.m. We do it because we got to find a time where you put 300 people in one room. Okay, but again, this is the unscheduled block. So nobody should have an academic conflict with this exam. Okay, so 1 to 3 p.m. on the Thursday of finals week, which really, it's the optimal time. We wanted to set it up so that if what you needed to do was, turn in the performance of your life in order to get the grade you needed in this class, where do you put the final to make that possible? You put it towards the end of the week, in the middle of the day, where you can get a good night's sleep before, where we can have review sessions all week long before that, office hours all week. I mean, that's it. The ball's in your court, guys. Okay, so if you turned in 2 consecutive bad exams, right, and your grade is not very good, and you're like on this edge, can I even get a C in here, or am I going to have to come back in the spring? I mean, this is your chance. I don't want anybody back in the spring. Okay? I'm sure the staff will be seeing some of you. I don't want it to happen. Okay, so whatever it is that you can do to do that. And then at the same time, just whatever grade you want to get. Okay, and the final warning, if you turned in 2 consecutive high grades, I'm not worried about you, but don't rest on your laurels, right? Because most people that turn in 2 consecutive high grades in here had an awful lot of math previously, is usually what happens, not always the case. Okay, almost nobody in here has really had differential equations and some of these applications of integrals that we've done. Okay, so just make sure you understand, if the stuff on exam 2 was new for you, you never had that kind of math and you still nailed it, well then you know what you're doing in terms of preparation and getting ready, mastering new stuff and being able to perform. But if you had AP Calc 1 and 2 already and it just wasn't that big of a stretch for you, realize this is more new stuff we're still doing. Don't blow it off. I'd hate to see a strong student end up with a B in here because they just blow off the final and have a terrible day. Okay? Is that enough? Big picture, motivation? All right. And then obviously, MATLAB finals are coming up, right, during the last week. So you guys will have that as well. Your TAs should be talking about the procedures for that. Okay, in lab, regular lab meeting. All right, so I'm going to go ahead and pass around a sheet that we'll get to. Listen up, guys. Shortly, this is the recipe for how to solve a differential equation. Now, we will get to this just like we do all problems in here. We're going to start by working an example, okay? And we're going to get to a point where it becomes necessary to explain how to actually solve a differential equation. Okay, that point will happen sooner rather than later. And so if we could just go ahead and start passing this around, just grab one and pass it on. There's an awful lot of writing on this piece of paper, okay? It's a recipe. So what I really want to focus on is that you guys really understand the reasons behind all of these steps. Okay, if you guys are going to be successful engineering students, which I know you all can be, okay, then what you want to get away from is dependency on memorizing how to do stuff. All right, there's just too much information. So the most successful engineers and scientists of any type are people that don't have very good memories. Okay, you don't want to have a good memory. What you want to have is understanding. So when you look at something and you go, yeah, I don't really remember how to do that, you're not scared of that reality. You say, so I guess I'm going to have to sit down and figure it out, right? That's what we do, figure stuff out. So if you understand the reasons behind the steps in this recipe, then you're not going to have to memorize this whole procedure. It's going to be obvious to you, what do I do next, and why am I doing it, and that's it. And then it's just problem solving. Okay? So that's the plan. So we are going to move ahead with differential equations. We're going to look at a general form of the leaking bucket that you guys did in lab. And in fact, by the end of the class, we will get specific. We will turn it into the exact problem you did in lab. So we make sure we understand where that solution comes from. Okay, but I want to think about it in an even more general way to start out. So, topic is differential equations. Okay, and again, it is the leaking bucket is what we like to call it. Okay, and what do we mean by that? Well, in a general sense, I could have a bucket or some kind of container that has fluid going into the bucket. So first thing I want to think about is the idea that I can have a faucet or something on top, and I've actually got fluid coming in here. Okay, and so this is the bucket. Okay, and the fluid coming in will be characterized in terms of a volume flow. Okay, and so the things we're going to keep track of here is how much fluid do I have in the bucket, which we'll call that the height, h of t. Okay, and the reason why the height is a function of time is this problem can start out, at any level. The bucket could be empty, so the initial height of the fluid is 0. Right? Or I could start with a bucket that's full like you guys did in lab, and I could actually have fluid leaking out. So we got two things going on. Fluid coming in, okay, and fluid going out the nozzle here at the bottom. Okay, and so I've got some, some exit valve or something there. Okay, so here's what I want to define. A couple problem parameters. Number one, this container's got some kind of a cross-sectional area. Okay, and so I'm going to call the area of the container the cross-sectional area A. So, for example, if this is a cylindrical container, then that cross-section would be a circle, right? The area, if I looked at it from a top view. But it doesn't have to be cylindrical. I mean, it could be any prismatic shape that I want. It could be a rectangular container. It could be some kind of hopper, whatever. Okay, and then if I've got an area A, right, and I've got a height over here, then combination of those two things gives me a volume of liquid inside here, V. So I've got volume as well. Okay, and then finally I'll define my fluid flow. The fluid coming in engineering we like to use the letter Q for volume flows, so we're going to call this Q in. That's the volume flow coming in. Okay, and down here at the bottom, we're going to call this Q out. That's the volume flow going out. Okay, and I want to build in a basic principle into this picture here. Okay, and this is almost like, this is called the leaking bucket, but almost thinking about this as if it were a bathtub, right? Like if you turned on the water in an empty bathtub, okay, and the drain was partially open, but you really like cranked on this water, right? Then the water would really be pouring in here at a pretty high rate of Q in, and it probably wouldn't drain out as fast as it's coming in. So what would happen to the volume in the bucket then, or the bathtub? It would start raising over time, right? And so really a fundamental physical question might be, like, am I going to overflow the bathtub here? Right? Because as the volume starts getting bigger, do you think it keeps going out at the same rate down here? Why not? Pressure from the water, right? So initially there's no water in here. So it's just kind of dribbling out. And then as I start to build up this water, just like we talked about in the dam problem, right? And the distributed load problem, I start to build up pressure here. So clearly I'm going to force more fluid out the bottom with some pressure. Okay? And so what I'm going to do for this Q out is I'm going to say it's proportional to the height. And this is kind of a simplistic way to think about it. But I'm going to say it's some constant K times the height, times h of t. That way, the higher this thing gets, the more Q out I get, which makes some physical sense, right? Because of the extra pressure. All right, so we're getting there. Okay, what do you think that K depends on? The area of what? This one? The drain. The drain, right? Like if I have a little bitty valve, then clearly if I have more pressure, it'll still come out faster. But if I make the valve twice as big, then maybe the K is effectively twice as big now. All right, so yeah, clearly the geometry of the drain has to do with the K right here. But what else? Like what if the bathtub was filled with maple syrup as opposed to water? Yeah, it's the fluid properties, right? He said viscosity, right? Fancy word for how thick stuff is when it flows, okay? But a really thick fluid's not going to be coming out at the same volume rate as water would, okay? So K, this is a simplistic model for the problem, but basically K, this depends essentially on whatever the fluid is, okay? On the fluid, okay? And also the valve geometry. Okay, and you might be able to think of other things it could depend on, like, am I conducting this experiment on Earth or on the moon, for example? Okay, that might factor in there as well. Right, so it's got to be related to the pressure, the net effect on the fluid, the valve geometry, but we will settle for the idea that the Q out is proportional to the height. Okay, recognizing that the height changes as more fluid builds up in there. All right, do we have a pretty good comfort level for the physics here? So what we would like to get to is a model that would allow me to solve for the height as a function of time, right? If this is a bathtub and I'm worried about overflowing this thing, do I need to replace the living room ceiling, right? I might have to if this thing's just going to overflow and continuously fill the second floor with water. Okay? And so the question is, you know, what's h as a function of time? Is it okay to let this thing run? Right? Am I going to reach a point where this thing raises enough? Right? How do I know when it's not going to raise anymore?
When Q in and Q out are the same.
Sure. When Q in and Q out are the same. So the statement is, there's going to be some portion of time where Q in and Q out are not the same. That's when I'm adding volume to the tank. But then at some point, I build up enough pressure in here that the Q out balances the Q in, and the liquid will stay at a steady state. And as long as that steady state height is less than the height of the bathtub, then I'm in good shape, right? But if that height is over the top here, then I've got a problem. Okay, so clearly you could come up with this model and answer that kind of question for any container, bathtub, whatever. All right, so we're going to need some kind of equation to solve for the h of t. So in engineering in general, we like to start from basic physical principles, right? Is there a physical principle that I could articulate, and then can we write that down in terms of math? Can somebody tell me in words? You know, you've already described, you know, what kind of would happen when this thing stops rising, whatever. Can somebody describe for me in words, you know, what would be a description of the change in volume in that tank? Have a crack. Yes? All right, so the volume as a function of time, I actually like that, right? We can say this. It's a function of time because just like the area of a cylinder, right? Pi r squared h. No matter what the shape of this is, the way you get a volume is you take the cross-section area and you sweep it through the height, right? If it's a prismatic kind of shape, right? All the cross-sections are the same. Okay, so yeah, I could take area times height and the volume is a function of time. So what would be the principle, do you think, that would give me an equation for h? You already told me the steady state outcome. When Q in equals Q out, then the change in volume is what? 0. Okay, so what if Q in doesn't equal Q out?
Q in minus Q out equals volume as a function of time.
Close. Okay, so maybe I need to define these a little better. Q is what we call a volume flow rate, okay? Not an actual volume. So can anybody relate for me what might be a unit on a volume flow rate?
Milliliters per second.
Yeah, milliliters per second. Right, what about at the gas pump? What do they use there?
Gallons.
Gallons per? Is it gallons per mile? Is gallons per mile a rate? That's like the inverse of your gas mileage, right? So you're on the right track. It's gasoline. Gallons per what?
Dollar.
Gallons per dollar. It's a statement of how poor you're going to be when you're done at the pump. What's the unit? No, you guys put gas in your cars, right? What's the unit?
Gallons per minute.
Gallons per minute. They use a flow meter gallons per minute. It's a volume gallon per unit time. Okay, the other one is, only the guys in here appreciate this. right? So every time you go to the bathroom, there's a unit on the urinal. What's on there? They don't put this on the seated toilets. It's just, so what is it?
Liters per flush.
Not, well,
Gallons per flush.
yeah, it's the GPF, right? Gallons per flush, okay? So that is kind of a rate also, if you think about a flush as a rate, okay? All right, so it is a flow rate. So back to your explanation again. This is, for example, you know, cubic meters per second, right? So back to your explanation. Can we try that again? You said Q in minus Q out is the volume. It's dV dt. It's the rate of change of the volume, right? Because the Q's themselves are rates. Okay, so this is the starting point, right? And so this is what we call our governing principle. Okay, and essentially what it is, as was said, Q in minus Q out. If I've got more fluid coming in than I have going out, then I've got to have a change in volume, right? And so this is going to be the derivative dV dt. Okay, that's it. Incidentally, just a small comment, right? This would be true if I have what's called an incompressible fluid here, right? In fact, the real governing law, you guys all took some high school science, right? It's a conservation law, right? Like, for example, conservation of energy. What's actually being conserved in an argument like this? Amount of water. That's not wrong. Can you be more specific instead of the word amount? Potential energy. Okay, so if you want to consider the dynamics of the fluid, then energy is part of it. And yes, potential energy, how fast it's coming out, kinetic energy, yes. This principle right here, though, is not energy conservation. This is conservation of what? Yeah, so I just wanted to make the point that there is no law that says volume has to be conserved. Volume is not a basic unit of matter. Right? So for example, I could have some process where I put something in as a liquid and it comes out as a gas. Volume conserved? Gas takes up a lot more volume, right? So it's not that, it's mass. I mean, the numbers of atoms have to be conserved, right? So the mass, I mean, even that, a chemist would go after me, right? The mass has to be conserved. Whatever matter comes in, the matter has to go out. So the point is, if this is water or syrup or whatever, and it's basically incompressible, it means that even if I build up pressure, I'm not changing the density. Okay, the density of the water is the same no matter what the pressure. That's called incompressible flow. Okay, you'll learn more about this in fluids type class. All right, so Q in minus Q out, conservation of volume is true as long as the density is always constant. Okay, good. So now we're getting somewhere. So can we get an equation for the height as a function of time? Let me ask you this. Does Q in depend on the height? This is what I control, right? This can be anything. I could be over here with the knob. I've done this on the final exam, by the way. I could be over here with the knob, back and forth in a sinusoidal fashion, okay? I could have a sinusoidal Q in right here, no problem. Or I could just turn it on and let it run. What kind of function would that be? That'd be a constant. Q in's a constant. Or somebody said linear. Linear would be like very slowly turning the knob at a steady pace, right? At a linear pace. Or I could turn the knob at a quadratic pace, right? I mean, so you could make this Q in whatever you want. Okay, but the point is, Q in doesn't depend on H. I control Q in. How about Q out? Yeah, I mean, so this guy depends on the height. So this is K, H of T, so we'll have a height in there. What about that volume term? Does that depend on H? Yeah, because volume, this is the derivative of the volume. What's the volume? Yeah, it's the cross-sectional area multiplied by the height. So I'm really taking the derivative of the cross-sectional area times the height now. Now what about that cross-sectional area? Is that a constant? Yeah, I mean it is, right? So now, does it have to be? Or could I have a curve, a shape like this where it's tapered or something? I could have that. That makes the problem more complicated. Okay, but so for the purpose of this, let's say it's prismatic, right? All the cross sections are the same, no matter what the shape. Then the area happens, what do I do with this? I can pull it out front, right? So now we've reached this point, Q in minus Q out, which is K h of t, is equal to this derivative. The A can come out front, and then I'm going to have this derivative dh dt. So you take a look there, okay, and now what I have is an equation that's got Q in, something I independently control. It's got a problem parameter K, depends on the fluid, depends on the valve, it's a parameter of the problem. It's got the height, it's got the cross-sectional area of the tank, that's a problem parameter, and then it's got a derivative of the height. So this is one equation with an unknown function h and a derivative of h. That's what a differential equation is. It's an equation that has an unknown function and one or more of its derivatives. A first derivative, a second derivative, a first and a second derivative, right? I can have all of these things in one equation, okay? And so the final thing that I would note is that there's a standard form we like to write this in. We like to put the unknown function and its derivatives all on one side of the equation, all right? Just like we do in equation solving in general. Isolate what you want to find, right? And then find it. So we'll put the h and everything else on one side. So on the left, I'm going to have this term, A dh dt, right? And then I'm going to move this term over, plus K times h of t, okay, is equal to this input function, Q in. Okay, and that, okay, will be my first order differential equation. Okay, so this is called a first order differential equation. Okay, and by the way, we like to use this abbreviation DEQ, okay, for differential equation. It's a first order differential equation, and I want to describe it one step further. Okay, if you note on this equation, I've got h of t, and I have a derivative dh dt. And then I've got these parameters in there. These parameters are constants, right? They don't depend on h, and they don't depend on t at all. So if you have that, this equation is an equation with what's called constant coefficients. It means whatever letters are in front of the h's and the derivatives of h, okay, those letters are constant parameters, constants. Don't depend on time, don't depend on h. Okay, that's the key thing. I'll add one more word. That's this one, linear. So this is a first order linear differential equation with constant coefficients. The word linear here does not mean y equals mx plus b, just to be clear. What makes a differential equation not linear, okay, is if these terms are not linear combinations of h and its derivatives. So in other words, what if this term was the square root of h, or h squared? Then I don't have just h and its derivatives. I got h squared and its derivative, right? Or what if I had an h right here that multiplied the dh dt, right? So any of these things mean it's not linear. In other words, if I double everything, the 2 goes right through the whole equation, all right? That's what we mean by linear, okay? Linear combination. So if my equation only has the function itself and derivatives of the function that are added up in a linear way, I don't have any square roots, I don't have any squareds, I don't have any of this stuff, and if the coefficients are constant. Then this is important. No matter how many derivatives are in here, I could have a second derivative, I could have a third derivative, I could have all these derivatives. The procedure to solve these equations is always the same. Always the same. And it is the recipe that I handed out. Okay, so what we're going to do is we're going to go through this recipe, and I'm going to try and give you the whys of the recipe first. And I know that you won't completely buy into the arguments until we actually start solving the real equation. So we'll get back to that part as soon as possible. But we have reached the point where we need to be able to solve a linear differential equation with constant coefficients. Before I talk about the recipe, any questions about this problem we're trying to solve here, okay, or about my definition of what this is? Good? Okay, by the way, 90% of all problems that you will see in a textbook, you know, to develop electrical engineering, mechanical engineering, biomedical, whatever, okay, in engineering are linear equations with constant coefficients. All right, so we are going to have you take an entire semester class in differential equations with matrix algebra, which makes the differential equations class much, much more useful. Okay, and the reason that is because 90% of all the problems you're going to solve by hand when you're a college student are like this. Okay, and listen to this very carefully. 100% of real problems are nonlinear and can't be solved exactly by hand and have to be solved by numerical methods, which requires matrix methods. Okay? So, now does that mean that this is a waste of your time to learn this? No. I mean, we're going to see all kinds of like major physics that we can predict, actual phenomenon that's responsible for things like bridges falling down that we can get from these linear models, which approximate real life. Okay? But most of the hard problems in engineering, all the easy stuff's in the textbooks. Okay? And so the real stuff, like I work for an automaker and I got some vibrations in my engine or whatever, and you know, or the brakes are squealing and I got to figure that out, or whatever it is. These problems have to be modeled in 3 dimensions and solved numerically. I can't get a hand solution. Okay? So the hand solutions are all about understanding the fundamentals of the theory that you're going to learn in your classes moving forward, but then you got to appreciate the idea that your real problems, you're going to need to be throwing software at it, numerical methods at it to get it done. Okay? So that's the big picture. All right, so moving ahead, let's talk about how do you solve a differential equation. All right, so you guys all have the sheet here, okay, which is your recipe. And just like when we had the derivative sheet and the integral sheet, you really ought to have this thing out for really the rest of the lectures. I hope we reach the point where it's kind of old hat. But this is just a summary, and this is really an excerpt right out of the textbook anyway, okay, on our chapter on differential equations. But in the most general sense, a differential equation is if I got an unknown function, my output variable, in this case, h of t, right? An output variable, let's say y of t, and its derivatives. So this notation, it means the nth derivative. This could be the 3rd derivative, the 4th derivative. It doesn't matter how many derivatives. I have them all lined up with coefficients and derivatives, but it is a linear combination here in general. Okay? And it equals something else. The something else is anything that doesn't have a y or a derivative of y. So when you do a governing principle and you write down this physical equation, you know, how do you know what's the left side and what's the right side? Whatever your unknown function is and its derivatives, that all goes on the left, right? Whatever's left on the right is your forcing function. So in our case, that f of t is the q in, right? It's the knob. It's me turning the knob to make the volume flow in. So here's the thing. In the most general sense, these letter A's, they can be constants or they can be functions of y, in which case this is not linear now, right? Or they can be functions of time, in which case, you know, it just becomes more complicated to solve. Okay, and the f of t is called the forcing function. Okay. So, for example, in a dynamics problem, we already talked extensively in here, right? All semester it seems like. Position, velocity, acceleration. Okay, perfect example. Acceleration is a second derivative of position. Velocity is a first derivative of position. Position is the 0th derivative, right? The function itself. So the point is, if I have an oscillating system, something with a spring and a mass and a damper on it, then I would get this general second order equation here. And if I were forcing that with a literal force on it, well, that force would end up being the forcing function on the right hand side. Okay, so dynamics is an easy way to think about it. Couple things notationally. This takes a lot of ink. Okay? Writing out the second derivative, the first derivative, and you do a lot of writing in your classes. So engineers decided, you know what, we're going to use dots instead. Now, just to be clear, if you've had calculus before, whether in college or high school, in calculus they like to use a prime, right? Even on the back of the derivative sheet I handed out, there was formulas for f prime of x. Here's the general convention. When you take spatial derivatives like dy dx, derivative with respect to x, primes are used for spatial derivatives. Dots, pretty universally used for time derivatives. So y dot means dy dt. Y double dot means the second derivative. Okay, so in engineering books, classrooms, whatever, even in math departments, you'll see the dot notation used. Pretty much standard. Okay, so we do it just to simplify life. So back to the dynamics problem. We've talked in here already about springs and masses and such, and you know, you'll be doing the lab, already are doing the lab on this. And here's the governing equation for a spring mass system. M's the mass, y double dot's the acceleration, right? So this is force equals ma. So here's the ma, here's a spring force, k times y. Here's the forcing function, f of t. So it's just a statement of f equals ma when I have an oscillating dynamic system. Okay? And so that's a classic example. We will solve, by the way, in the next couple lectures, we will be solving the entire solution to a forced vibration of a spring mass system. Okay, get a lot of insights from that solution. Okay, and so, you know, again, if those coefficients are functions of y or t, there's some methods you can use to get an exact solution by hand, but it's a limited subset of methods that just happen to work for certain types of problems. In general, particularly if they're functions of y and the thing is nonlinear, you got to use numerical methods, differential equation solvers in MATLAB. Okay, so you'll have some homework that has this stuff in it. Okay, if the coefficients are constants, like a spring mass, m is the mass, it's a constant. K is the spring stiffness, it's a constant. In our problem here, I've got K, which is the fluid in the valve. I've got A, which is the area. These are constants. Okay, if that is true, then the solution to a differential equation of any order, first order, second order, third order, no matter how many derivatives, it is all the procedure outlined on this page. Okay, and it's 3 steps. All right, you look at what you've got here. It's a step 1 in bold, then there's a step 2 in bold, and then there's a step 3. So 3 overall steps that all have a bunch of subsets. Okay, so this is our plan. Questions on the big picture before we go through this recipe? All right, so again, my goal here is to get through what the steps are and try and explain the why so we don't have to memorize the steps. Okay, and then as we move forward, we'll be doing leaking bucket today, hopefully finishing up. If not, finish next time. Then we'll be doing spring mass, right? And then we'll be doing circuits in electrical. So we're going to solve a lot of these differential equations, and you'll have the homework. If you understand the why, the method just really becomes kind of second nature, right? So it's not memorizing this sheet. All right, so what do? Step number 1. Take your original equation, okay? Your original equation has a forcing function on the right-hand side, right? Here it is, f of t on the right-hand side. Step number 1 is to pretend that you don't have the forcing function. make it 0. Okay? And so the question is, why would I do that? Okay? This step is called, in engineering, we call it finding the transient solution. That'll become clear why. Does anybody have a definition for the word transient? If I say something is transient, what does that mean? Say again? Passing, right? Like it doesn't go on forever. Dies out over time. So think about some of the problems physically that could be governed by this. Like the leaking bucket, right? Is there any liquid left in it after it runs out? Kind of gone, right? So it goes over time, it is gone. Okay, RC kind of circuit. Discharge a capacitor. The electricity flows out. It's like a leaking bucket, right? Except it's electrons instead of water. Same thing, right? So there's all kinds of behaviors of physical systems that are time dependent, but that part of the solution only lasts for a certain amount of time and then it's gone. That's what we mean by transient, okay? So, how do I find that? Well, in a math department, this is really important because what can confuse kids about differential equations is all the terminology for the same thing. In engineering, we like to call this transient. In a math book, they will call it two different things. They'll call it the homogeneous solution, and they'll also call it the complementary solution. All three of these words mean the same thing. Transient, complementary, homogeneous. The words don't literally mean the same thing, but the step means the same thing. It means make the right-hand side 0. Okay, so the reason for the words, homogeneous in math is a term that basically means the right-hand side is 0. So that's the literal definition. Complementary is the one I like better. Okay? And here's why. If I'm going to add up a whole bunch of terms and get 0. Okay, forget that we're talking about differential equations. Any equation. If I want to add up a bunch of terms and get 0, from an algebra standpoint, what can you tell me about the terms? They're all what?
They're opposite in signs, and you're adding them up.
Okay, so some have to be opposite in signs. That's probably true. You got to have some opposite signs. So let me ask a leading question. Can I add combinations of x cubed and x squared and get 0?
No.
Why not? All right, so algebraically I can only add stuff that's what? Just looking for the right language here. I can only add what? Like terms. I got to have like terms. All right, so here's the thing. If there exists a function y, okay, this is important, that when I take the function and I take its derivatives and I can add it all up and get 0, then it has to be a function that gives me like terms when I take its derivative. What function, when I take its derivative, gives me the same function again? E. E to the st. So here's the thing. This word complementary, here's the corollary to what I just said. This is not my real problem. My real problem has f over here, right? So if I had the right answer when I took the function and its derivatives and I got f, couldn't I also add a function that when I took the function and added all its derivatives, I got nothing? You guys follow me here? If there's a solution that gives me the f, and there's another possible solution that gives me nothing, then when I add the two solutions together, because this is linear, a linear combination, when I take the derivative of the sum, it's the sum of the derivatives. So part of the solution gives me nothing. The other part gives me f. If I forget the part that gives me nothing, then I'm missing part of the answer. So it's the complementary part, right? It's the part that the solution's not complete if I don't get this part. So the procedure is, we already know out of the gate that part of this answer doesn't give me f, it gives me nothing. So I'm going to find that first so I can make sure I include that. right? And once I include that, we'll call that the complementary. Now, because the only function this will work for is the exponential function, exponential functions are like e to the st. If s is a negative number, what does that function look like over time? Decays to nothing. It's transient, right? So we call this the transient solution because of the nature of the functions that work for this, right? It's functions that die out over time. Transient behavior, decaying capacitor, leaking fluid out of the bucket. Keep in mind, there's other exponentials, right? Like what if e to the st, what if the s is imaginary? J, something j. Is e to the j theta a decaying response? What's e to the j theta? See, we don't cover anything in here, right? That's not used again. What's e to the j theta? Euler. Who remembers the Euler formula? E to the j theta is what? Say again? Nope, not 1. E to the j theta. Remember? Shorthand for polar form. It's the exponential form. Literally, what is e to the j theta equal to? Cosine theta plus j sine theta. So transient solutions could be decaying, s is a negative number, or it could be oscillating, right? Be oscillating because it's sines and cosines. Okay, so either way, it's all exponential functions, and when I take the function and its derivatives and add them all up, I can get like terms, right? Think about sine and cosine. Take derivative of sine, what do I get? Cosine. Take another derivative, what do I get? Ooh, back to sine. Now I got like terms. Okay, so oscillating systems, spring mass kind of systems, you're looking in lab now, yeah, the solution's exponential, but it's actually a complex exponential, and it oscillates, sines and cosines. Okay, so no matter what, whether it's oscillating, whether it's decaying, all of this is transient. It's complementary because it's the part that gives me nothing. I have to add it to the part that gives me something to make the solution complete. Okay, so that's it. So here's what I do. Always, I know there's only one kind of function this works for, e to the st. So I forget the forcing function, make it 0. And what I want to know is, what's the s? What's the s in the e to the st that'll make this work? How do you find out? Plug it in. Right? So no matter what the equation is, no matter what the parameters, how many derivatives, you always set the right-hand side to 0 and substitute e to the st into the left-hand side. When I do that, I will have like terms. Every single term will have e to the st in it. If that's true, then what can I do with the e to the st? I can pull it out front. I factor it out. And if I could factor it out, look what I'm going to get left, right? One derivative, I'll get an s. Two derivatives, I'll get an s squared. Three derivatives, I'd get an s cubed. When I pull the e to the st out of every one of these terms, I'm going to have a polynomial. That's what's going to be left. A polynomial for s. Okay, and so I'll get something that looks like this. So I started with a differential equation, but now I got an algebraic equation. I might need to factor, right? I might need to do the quadratic formula, whatever it is, right? I got to use some algebra to find the s values that make this work. If it's a first order equation, I'm only going to have one s. right, there's a first derivative term. The s will come down. That's it. I solve for s. If it's a second order equation, I got a second derivative. I'll have an s squared. If I have a first derivative, I'll have an s also. So I'll have to solve the quadratic. So whatever numbers of s's I have, right, the right-hand side's 0. I'm finding the roots of the polynomial. Right, so I'll get different numbers for s, s1, s2, whatever, however many numbers. Okay, and so the idea is, once I have those numbers, s1 not necessarily the same as s2, etc., then my solution, there's more than one. E to the st is the answer. If s1's a root, then e to the s1t is the answer. So is e to the s2t, if I got two roots. They're all answers. Here's the key thing. The equation is a linear equation. It's a linear combination. So if e to the s1t works, and if e to the s2t works, then doesn't e to the s1t plus e to the s2t work? The derivative of the sum is the sum of the derivatives, right? So if I combine the two and plug it in, it still works. I can still combine like terms and get 0. So the most general solution is a combination, and keep in mind, the right side's 0, so any constant in front would be in every single term, and I could cancel it out. Just like when you do an indefinite integral, I can add whatever constant I want. So the point is, because it's a linear equation with constant coefficients, once I find the s values, the transient solution in the most general way is a linear combination. C1 e to the s1t plus C2 e to the s2t, however many s's I have, is the same as the order of the equation. First order equation, there's just one s. Second order equation, there's going to be two s's. Third order equation, I'd have 3. My solution is a linear combination of these. The c's are not known yet. Any constant will satisfy that. One special case that we will not see in this class, but if I didn't put it on here, I wouldn't have a complete treatment, so we stuck it on. Turns out that I can have a repeated root, right? So s1 and s2 are both the same number. So then if I would have c1 e to the s1t plus c2 e to the s1t, that's the same as c3 e to the s1t. I mean, there's no extra solution. So it turns out, mathematicians can show if I just add a linear term in here, this will be as general as you can make this. Okay, and so this is a special case. You will see that in differential equations class. Okay, and you'll see how that works. But in here, we can solve plenty of problems without worrying about that special case. Okay, just wanted you to be aware. All right, so questions about transient solution. Set the right-hand side to 0, sub e to the st, solve for s. That's it. All right, next step. What I have found so far is the part of the solution that gives me nothing. It does not give me f of t, which is the right-hand side. So I'm not done yet. I need the particular solution, right? That's what the math department calls it. The particular solution for my f of t. In engineering, we like to call that the steady state solution, because here's why. If the other part dies out, in the end, I got to be left with f of t, right? Or the equation's not true. So once the transient part's gone, I got to have something that's there forever, okay? And whatever that is, that's steady state. It means there in the long term, okay? And so that's what we find next. So there is again, an engineering kind of approach to finding this guy. Here's what you do. You go back to your original equation, okay? So now, the original equation has a right-hand side with an f, right? Here it is. I got an f on the right-hand side. And I'm trying to add a function and its derivatives to give me an f. So, for example, let's say the f is sinusoidal. Can I add up polynomials, t squared, t cubed, to give me sine omega t?
I don't think it works like that.
It doesn't work like that, right? If the right-hand side is polynomials, right, can I add up sines and cosines to give me a polynomial. Doesn't work like that, right? So the point is, this is like, it's an engineering solution. What kind of function can I find that when I add it up gives me the same function on the other side, right? I'm trying to find what gives me f. So here's how you do this. You take a look at the f, and you say, well, if the forcing function's constant, then why don't I just assume the steady state solution's a constant, plug it in, and see what I get. Okay. If the input function is linear, t to the first power, why don't I assume the most general linear function I can have, y equals mx plus b, at plus b, right? A and b, not known yet. They're undetermined coefficients. How do I determine them? I plug them into the equation and figure out what they have to be to make the right side equal the left. This is not like a theoretical solution. This is like an engineering solution. I'm just trying to find a function that works. Okay? Kt squared. Well, this is a parabola, so why don't I try the most general parabola? Either sine or cosine or a combination of the two for the forcing function. Let's assume the most general sine and cosine. A sine omega t, b cosine omega t. Note, if my forcing function has frequency omega, I better have the same omega in my steady state solution. I can't take a sine of 3t and add it to a sine of 2t and get a sine of 5t. The math doesn't work that way, right? I can't add them. They're not like terms. So what it means is physically, if I force something at a certain frequency, how do you think it behaves in the steady state? Same frequency, right? It's kind of common sense, right? I shake it like this. Well, yeah, over time it's going to start shaking the same way I'm shaking it, okay? And so we'll talk about the different behaviors that happens. All right, so that's it. So you assume a solution, and then you plug it in, and you do the algebra to try and find the a's and b's. Something both these steps have in common. It's a differential equation, but neither of these steps really involves further calculus. I'm turning equations with derivatives into equations filled with algebra and trig. Okay? That's what the actual math is to solve these. It's manipulating algebra, manipulating trig, trying to find a's and b's. That's what we're doing. All right, so once I have this, I now got two parts of a solution. I got a transient part, y transient of t, which is exponentials. I got a steady state part, y steady state, which depends on the forcing function. It looks like the forcing function. So the most general solution is the sum of the two. Why is it the sum of the two? Well, because when I plug this one in, I get what? 0. That's how I found this one. What's the function that when I plug it in, I get nothing? So clearly, if I add that to this one, this is the function that when I plug it in, I get f of t. So when I add them both, because the equation is linear and the derivative of the sum is the sum of the derivatives, because of that, the solution is the sum of the two. Note that this one still has unknown constants in it. I'm still stuck with this C1 and C2 back from step 1. So the very last step is, once I have the form of the functions that work, I need the exact functions that work, and that depends on the starting point. So to get the C's, I got to have initial conditions. If it's a first order problem, I got C1 unknown. How many initial conditions do I need? 1, right? 1 unknown. I need a starting point. If it's a second order problem, like a spring mass, position, velocity, acceleration, I got C1 and I got C2. How many conditions do I need? 2. And so again, it's not that hard, okay? It's tedious, not that hard. All right, so I need 2 conditions, and I got to apply the conditions that are based on physical statements. Where did I start? What was the initial velocity? What was the initial position? Great, now I got 2 conditions. Okay, in general, the conditions, this is important, are on the function itself and or a derivative of the function. If it's a second order equation, it won't be a condition on the second derivative. That condition is built into the equation. Right? The equation has the second derivative in it. Right? So these initial conditions are always a derivative down. Right? Third order equation, I'd need 3 conditions somehow. Right? It's not a physical problem because there is no third order of acceleration. Right? But if you had that, you need 1 on the position, the first derivative and the second. Okay, so in general, guys, initial conditions are first order problem, I need the starting point. Second order problem, I need the starting point and the t equals 0 for the derivative of the function. Right? So in dynamics, I need an initial position, I need an initial velocity, and then I can get the dynamics. This is the recipe. Admittedly tedious. Okay, so last time I will go through the recipe. What we will do is apply the recipe to the solution of multiple problems for the next 4 lectures. I want to get back to the one we started, that we can at least get the general solution taken care of here today. So, leaking bucket. I got a method I use when we do differential equations because it is, in terms of the math sequence, it's the most advanced topic, even though I think I've said repeatedly in here that I don't think it's the most conceptually difficult topic, but it is the one that is furthest down the math sequence. Okay, and because of that, I need to be absolutely certain that we all know what's going on when we solve these things. Okay, and so I've got a procedure for doing this. A, I'm not writing anything down until somebody in the room tells me what it's going to be. I'll ask the question. And B, you're not allowed to answer me more than once. Okay? So those are the 2 rules. We're going to do this throughout. So here's my equation, okay, that I would like to solve. I'm going to transcribe it back here so we can do the solution there. So it's A dh dt, right, plus K h of t, okay, is equal to a forcing function Qn. Okay, we'll talk more about different types of initial conditions I could have, but I want to just move forward with the solution procedure. So whoever answers my first question, you know, this is the easiest question, right? What's step 1? Qn to be f of t. All right, so step 1 is the transient solution. Okay, and again, I'm going to set f of t equal to 0. Now, what's the f of t in this problem? Yeah, so for this problem, Qn equals 0, right? That's the interpretation. So every problem's got a different f of t. Again, how do you know what the f is? Everything with the unknown function and its derivatives is on the left. Everything else is the f. This is the f because it doesn't have an h or its derivative in it. Okay? So, great. Good. A dh dt plus k h of t now equals 0. Okay? What do you think? Next step. It's all on the sheet, right? So you can just read as we go. All right, so substitute e to the st. You're done. I don't want to hear from you again. Substitute e to the st. Okay, so you know what we will do is we will let, right, the transient solution h transient of t. This says trans right here, equal e to the st. And the point is, I'm going to plug this in wherever I see an h. So the first term, a times that derivative, right? So I'll write it out, actually. I need the derivative, right, of e to the st. All right? Okay, plus k times the function itself, e to the st, is equal to 0. Good. So what's the derivative of e to the st? Is it 1 over s? It's just s, right? So what I get here is a s e to the st, right, plus k e to the st equals 0. So at this point, after I substitute the e to the st, And mind you, the whole reason I'm using e to the st is so I can get like terms, right? What can I always do at this point in the solution? Factor it out. If I can't factor in e to the st right here, I just screwed something up. Okay? So e to the st comes out front, and what am I left with? A times s plus k equals 0. Now again, you know in here we like to do problems that have parameters, so you always want to be sure you're on top of like what the heck are all these letters. So just to be clear, what are we even trying to solve for here? Right here. Am I trying to solve for A? What's A? A is the area. That's a problem parameter. What am I trying to solve for? S. What about the K? That's a constant. It's the valve. Is it molasses or water, right? It's a problem parameter. All right, so I want to solve for this. So let me ask this question. Is e to the st ever equal to 0? No. Right? So this is always true. This is never 0. So there's only one possibility, right? That as plus k has to equal 0. Right? If the e to the st is not 0, then the rest of it has to be 0. How many solutions to that are there? There's just one. A is minus k divided by a, right? S, sorry, is minus k divided by a. Yes?
Yes.
All right, so I got an s. How many s's are there?
1.
That's S1. Okay? It's the only s. So I find all the possible s's. It's a first order equation. There's only one s. And that means the transient solution has to be then what? So in the most general sense, forget the a's and k's and everything. When I get an S1, then my transient solution is what? Where was that coming from? Heard something right. Over here, yeah.
C1 e to the st.
E to the S1t, whatever it is, right? So it's going to be C1 e to the S1t. So the point is I found the S1 that worked for this problem, right? So H transient for us, okay, for this problem is C1, which is unknown, and it's an exponential function. S1 is minus k divided by a times time. Okay, so this is the transient solution. You can put a box around it. In fact, on the final exam, that would be 5 points right there, right? Find me the transient solution, part A. So it's C1, unknown. It's an exponential. The exponent is minus k divided by a times time. All right, so what about the next part? That's the transient.
Steady state.
I need a steady state. Okay? And in order to do the steady state, I could rush through this and say, can I get this in 45 seconds? Or I could leave you guys hanging, and we could make sure we recap this and get the steady state on Thursday. Okay? Which is going to be the plan. 2 days of suspense. Yes, so we're going to keep going.